Hello people, my name is Rishi Dhoble and I welcome you all to this beautiful series QuRe, where we'll be revising the chapters relevant to the JEE syllabus. Before beginning, a little bit about myself. I got a rank of 3406 in my JEE Advance, a 9093 rank in JEE Mains and a KVPY Essex rank of 1586 in the year 2021. So without any further ado, let us begin with the chapter. Episode 1, Solutions. So let us begin with this wonderful chapter. So what exactly is a solution? It is the mixture of two or more liquids, solutes, etc. Solutions are of mainly two types: the homogeneous solutions and the heterogeneous solutions. One of the most important equations in this chapter is the Clausius-Clapeyron equation. Let me show you. It is the natural log of the ratio of final pressure and initial pressure equals to minus the vaporization enthalpy of the liquid in consideration upon the universal gas constant into 1 upon the final temperature minus 1 upon the initial temperature. There are two types of mixtures. First are the heterogeneous mixtures. They had different layers due to density difference. The second are the homogeneous mixtures. They have the same mixture throughout. They have uniform composition. This is something which we know since our earlier grades, so no need to elaborate any further. Now let us review some of the common concentration expression terms used in this chapter. The first is the mole fraction. It is denoted by the Greek letter chi. Now chi is equal to number of moles of the component into consideration upon total number of moles of the solution or the mixture. This can also be written as N1 upon summation of Ni, where I is equal to 1 till M, and M is the number of components present in the mixture. A key point to note over here is that the summation of the mole fractions of all the components present in the mixture will always come out to be 1. Please keep this point in mind, folks. The second is the mass percentage. Quite easy to understand. It is equal to mass of the component into consideration upon total mass of the mixture, that is M1 plus M2 plus N3, so on and so forth, multiplied by 100. Another important fact here is that volume percentage is exactly the same, conceptually as well as formula wise. The third one is the mass by volume percentage. This is defined as mass of the solute upon volume of the solution into 100. This is commonly used on medicine bottles. If there is a medicine bottle in your home, which I am sure it is, you should check it out. The fourth one is ppm, that is parts per million. Now this tiny little fella has been known to give a lot of trouble to a lot of students. ppm can be explained as particles of solute upon particles of the solution multiplied by 10 to the power 6, because we are talking about millions here, right? A point over here to note is that ppm can be expressed in milligram per liter. This is the standard denotation and it is quite easy to understand as well in the questions. So people, this is a very important slide because these terms are used extensively throughout the course. The first is molarity. Capital M is defined as number of moles of solute upon volume of the solution in liters. Quite easy to understand. And its brother, molality, small m, is defined as moles of the solute upon mass of the solvent in kilograms. Mind you, I repeat, mass of the solvent in kilograms. In the process of dissolution, there is a dynamic equilibrium between the solid and the dissolved state of solute. There is a continuous process of dissolution as well as recrystallization of the solute particles. On the basis of solubility, the solutions are divided into three categories. The first are the unsaturated solutions. The second are the saturated solutions. And the third are the supersaturated solutions. These are quite unstable in nature and more than the equilibrium amount of the solute is present in it. Let us talk about solubility. Solubility depends on three factors. First is the nature of solvent. Second is the pressure. Third is the temperature. Now, temperature gives rise to two interesting cases. First case is the endothermic case. Here, the solubility is directly proportional to the temperature. The second case is the exothermic case. Here, the solubility is inversely proportional to the temperature. This can be easily understood by the Le Chatelier's principle. In case 1, the heat involved is on the left hand side of the equilibrium. So increasing the temperature will drive the equilibrium forward, that is, increasing the solubility. In case 2, the heat is involved on the right hand side of the equation. Hence, increasing the temperature will drive the reaction backwards, hence decreasing the solubility of the reaction. Let us revise the Henry's law. It states that the solubility of a solute in a solution is directly proportional to the pressure above it. That is, mole fraction or solubility is directly proportional to the pressure, that is P. Now, Henry's law can be understood by Le Chatelier's principle, that is, solubility increases with pressure. Let us understand the equation behind Henry's law. Once we remove the proportionality, mole fraction is equal to Kh dot P. This Kh is something that we call as Henry's constant. Now, Henry's constant varies from solvent to solvent, from liquid to liquid. Kh is directly proportional to the temperature. We have already seen that the solubility, that is the mole fraction, and pressure have a linear dependency on each other. That is, chi and P are linearly dependent, as seen in the graph. This slide is quite theoretical in nature. It talks about the limitations or conditions under which the Henry's law is applicable, and quite a few of its applications in real life. Some of the most important points on this slide are bends in scuba divers. When the divers are underwater, there is a high pressure above them, which increases the solubility of gases present in their blood. But when they come back to the surface, the gases form bubbles, and this condition is quite painful. The second is anoxia. It is caused due to low amount of oxygen content in the blood. When we are on hills, there is low atmospheric pressure, so the solubility of oxygen in the blood decreases, and hence anoxia is caused. Let us now talk about the Raoult's law. It states that in a solution of volatile liquids, the partial vapor pressure of each component is directly proportional to its mole fraction in the liquid. Let me explain. Suppose this is the beaker, and this is the solution of the volatile liquids. Let us assume that the beaker is closed, so the gases accumulated are nothing but the volatile liquids. The pressure of these volatile liquids that have evaporated is given by this equation. That is, Pt, or the total pressure, is equal to P naught A, or the standard pressure of gas A, into mole fraction of A, that is chi A, plus P naught B into chi B. This simple equation is extensively used in the questions related to this chapter. We know from our discussion in the previous slides that chi A plus chi B is equal to 1. So, on substituting chi B is equal to 1 minus chi A in the above equation of the Raoult's law, we get Pt is equal to P naught A chi A plus P naught B into 1 minus chi A. On rearrangement, we get the following equation. That is, Pt is equal to P naught B plus P naught A minus P naught B into chi A. Now this equation shows us that there is a linear dependency of the total pressure on the mole fraction of one of the components. Another interesting question that arises is what is the individual pressure of the liquids present in the gaseous state. So, using the Dalton's law of partial pressures, we get that the partial pressure of liquid A is equal to Pt into Ya, where Ya is nothing but the mole fraction of liquid A present in the air. On rearrangement and substitution, we can see that Ya is nothing but P naught A chi A upon Pt. Quite simple to understand. And similarly, we can find the mole fraction of liquid B in the air. Another important fact to note that the enthalpy, the change in enthalpy of the mixture of the solution in Raoult's law is 0. The change in the volume of the mixture is also 0. The entropy is always increasing and the Gibbs enthalpy change is always decreasing, indicating that the process is spontaneous. The intermolecular forces between A and B is equal to the intermolecular forces between the molecules of A and B. As all things in nature, even the gases are not ideal, and hence they deviate from the Raoult's law. There are two types of deviations in Raoult's law. The first is the positive deviation. It so happens when the attractive forces between the molecules of liquid A and liquid B are weaker than the forces of attraction between the molecules of A and molecules of B independently. The change in enthalpy and the change in volume of the mixture is greater than 0 and hence positive deviation. The examples given below are quite important to remember. The second is the negative deviation. It happens when the molecules of A and B have strong attractive forces between them than the molecules of A and B independently. The change in enthalpy and the change in volume of the mixture is less than 0, hence negative deviation. The examples are listed below. Azeotropes. These are special types of Raoult's mixtures. They are basically the binary mixtures having same composition in liquid as well as vapor state and boil at constant temperature. Since they boil at constant temperature, they cannot be separated by distillation. There are two types of azeotropes. First are the maximum boiling azeotropes caused by negative deviation, and the second are the minimum boiling azeotropes caused due to positive deviation. Let us now talk about the colligative properties. This is the last and the most important part of this chapter. They are the properties of a solution which are only dependent on the number of particles of solute present and not on the nature of solute or solvent. Mind you, only dependent on the number of particles of solute. Another important factor over here to consider is the Van 't Hoff factor. It is the factor that takes into account the dissociation or the association of a solute in the solvent. Let us understand. Van 't Hoff factor, or I, is equal to the experimental or the observed colligative properties upon the theoretical or the expected colligative properties. This is also equal to the theoretical mass upon the observed mass. But the most used equation of Van 't Hoff factor is I is equal to 1 plus n minus 1 into alpha. Here, alpha is the degree of dissociation from the chemical equilibrium chapter, DOD or degree of dissociation, and n is the number of molecules into which the solute particles dissociate or associate. The first colligative property is the relative lowering of vapor pressure, or RLVP. Only when a non-volatile solute is added, that is, a solid solute, the overall pressure of the solvent is reduced. Why? Because the solute increases the entropy of the solution, so less vapor pressure is needed to achieve the stable entropy above it. Let us study the equation behind it. Raoult's law tells us that the pressure above the solution is equal to P naught A to chi A. Obviously, we will not be considering the pressure exerted by the solids because they do not. Let this be equation 1. Now the fact that we know that chi A plus chi of solute is equal to 1. Let this be equation 2. Combining 1 and 2, we get Pt is equal to P naught A into 1 minus mole fraction of solute. Let me go to the blank screen. On rearrangement, we get P naught A minus Pt upon P naught A equals the mole fraction of the solute. This, folks, is the equation of RLBP. Now another equation that we know is that the mole fraction of solute is equal to number of moles of solute upon the sum of the number of moles of solvent and solute. Using this equation here, we arrive at a much simpler equation, and that is P naught A minus Pt upon Pt is equal to number of moles of solute upon number of moles of the solvent. The second colligative property is the elevation of boiling point. Let us first understand what is boiling point. Boiling point is the temperature at which the vapor pressure of the liquid becomes equal to the external pressure or the atmospheric pressure. With this knowledge, we understand that due to RLBP, the vapor pressure of the solution decreases. So, the pressure to reach the P external is more. So, more heat is required and thus a rise in the boiling point. Look at this graph. The vapor pressure of the solution is quite less than that of the solvent. This extra heat is what is seen in the form of elevation of boiling point. Let us understand the equation. Delta Tb is equal to I dot Kb dot small m. I over here is the Van 't Hoff's factor. M is the molality, mind you, the temperature independent quantity, that is molality. And Kb is something that is known as the ebullioscopic constant. Quite a weird name. Ebullioscopic constant, more commonly known as the boiling point constant. This Kb can be understood as follows. Kb is equal to RTB square capital M upon 1000 delta H of vaporization. R here is the universal gas constant. Tb is the boiling point of the liquid in Kelvin. All the temperatures here are measured in Kelvin scale. M is the molar mass in kgs. Delta H of vaporization used here is in kilojoules. The third colligative property is the depression of freezing point. Since the vapor pressure is low, so lower temperature is needed to achieve the solid-liquid equilibrium as seen from the graph. This delta Tf is given by the equation I dot Kf dot small m. I is the Van 't Hoff's factor. M is the molality as in the previous case. And Kf is called as the cryoscopic constant. Whenever the word cryo comes up, understand that it is related to cold temperatures. Cryoscopic constant. Let us go to the blank screen. Kf can be expressed as RTF square capital M upon 1000 enthalpy of fusion, where Tf is the freezing point in Kelvin, similar to the ebullioscopic constant or the boiling point constant. The fourth colligative property is the osmotic pressure. Now this is a little bit of the theory behind the osmosis, something which we have already learned in class 9. The important takeaway over here
is the example of the semi-permeable membrane, that is cellulose acetate. Another important point to note is the osmotic pressure. Let us understand. Let us take a container and divide it into two parts. Both of them have water in it. One is a very concentrated solution, and the second one is the dilute solution, or simply water. So osmosis says that water will be driven from the right container to the left container. The pressure exerted in the left container just to stop the osmosis process is something known as the osmotic pressure, or OP. Quite interesting. And reverse osmosis, on the other hand, is when the pressure exerted on the left side of the container rises and is more than the osmotic pressure, then the water starts to flow in the right side. This is known as reverse osmosis, or RO. RO filtration plants. Everybody has that at homes, right? So let us now have a look at the equation of osmotic pressure. Osmotic pressure, or pi, is equal to CRT, where C is the concentration, mostly molarity, R is the universal gas constant, T is the temperature in Kelvin. Let us take an interesting example. Suppose there are two containers, container 1 and container 2. Container 1 has a volume V1 and concentration C1. Container 2 has a volume V2 and concentration C2. So the number of moles in container 1 is equal to C1V1, and the number of moles in container 2 is C2V2. The final concentration upon mixing these two becomes C final is equal to N1 plus N2 upon V1 plus V2. Basic. This also equals to C1V1 plus C2V2 upon V1 plus V2. On multiplying RT to both sides, we get RT into C final is equal to C1V1 plus C2V2 upon V1 plus V2 into RT. We can see the quantity on the left hand side is nothing but pi final, or the final osmotic pressure, pi F. This is equal to C1 RT into V1, that is pi 1 V1. Pi 1 V1 plus pi 2 V2 upon V1 plus V2, and hence we can find the combined osmotic pressure if two or more solutions are mixed together. Pretty simple. So people, this is the final slide of the presentation. It basically talks about the advantages of using the osmotic pressure in chemical labs. This is something that you can read on your own.
So with this, we conclude the episode 1 of QuRe Solutions. I hope you must have revised it efficiently. So people, that's it for today. Stay safe and remember, be limitless, because you are limitless.